Here is the filter for which I want a high impedance, low noise amplifier. To start with, I'm looking at the transmission through the filter from here to here, and then with a 1 PF capacitor from this point to the network analyzer or some other 50 ohm load. On resonance, the input impedance is a little bit inductive, so I will add an appropriate capacitor in series. That's not to get better transmission through the filter. Attenuation will change very little because there is a very small mismatch loss. But I want to avoid the phase shift. When I connect various signal sources, I will make them also 50 ohms. I know that the phase doesn't change because I'm going to measure the phase when converting this to an oscillator. 1.5 nanofarads is about right, sitting like this, and I'm using polypropylene because of the high Q and also because it doesn't add any noise. And here is the what I see on the input, 50 ohms and resistive, and the transmission hasn't changed. I'm sending 10 megahertz, 10 dBm into the unit, and I look at the output here on the oscilloscope, which is set to 50 ohms. And I have tuned very carefully for maximum on this signal, both the trimmers that set the frequency, this one and that one. 15 nanofarads and 8.2 ohms on the output gives me perfectly 50 ohms at 50 kilohertz offset. That's where I will measure the noise floor. In the close range, frequency span 1 kilohertz, you can see that the impedance is not 50 ohms. Marker 10 megahertz. I haven't tuned the filter after putting the transistor in place, so resonance is up here somewhere with a very large standing wave ratio on the output. But what I'm going to do now is to measure the noise at wide separations, and therefore I need 50 ohms at wide separations because the noise characteristics of the amplifier I have is calibrated for 50 ohms. Now I have connected the 50 ohm noise head to this low noise amplifier I have here, and I'm collecting the noise floor in Linrad. And then I move this connector to the output of this box here, and the noise floor to start with is well, here it is 0.27 and here 0.03. So I have something like 0.24 dB noise out with this configuration. And that is as a frequency separation of 50 kilohertz, where I know that the impedance is 50 ohms. I have retuned the output capacitor of the filter for maximum, and the voltage is not as high as before. The FET gives some loading, so now I have only 17.5 millivolts here. Here is the impedance on the output crystal, and I want it to be low to create very little noise in the field effect transistor. Now it is about 50 ohms and it's capacitive, but on the resonance it's almost zero. But I want it to be almost zero at 50 kilohertz instead. 0.82 microhenry is about right. And you can see it is about zero now on the low side, and it's low, 10 ohms or so on the high side. And the total span is 100 kilohertz, so this will be better. And I will now connect back the field effect transistor. This is the 50 ohm reference. That is the cold noise head of my noise figure meter. 0.039 now. It's drifting a little bit with time. 0.25 here. Well, I cannot say that this is a significant difference. Maybe it is a small difference, but I haven't measured accurately enough where the noise is. The impedance far from the resonance is still very close to 50 ohms, so the noise measurement is valid. But at close range, frequency span 1 kilohertz, I have a very ugly impedance like this. And this means that when I extract the signal, it will not come from a very low impedance. It comes from something which is resistive and also to the same amount roughly. I think it is inductive upwards. Marker 110. What? 10 megahertz. So that's the center frequency. And I have 500 nanohenries, that's 36 ohm inductive and 25 resistive. I have added a 1-to-1 transformer here to get a 180 degree phase shifted version of what I have on the source. And then I couple that to the gate with the trimmer. And I have adjusted the trimmer for the gate to source capacitance to be balanced out. The impedance I see on the output here looks like this. This is with a 1 kilohertz frequency sweep. To see anything I can magnify the scale. Scale 0.1, and this is what it looks like. So the impedance is not very much affected by what is connected to the gate anymore. At 10 dBm input, the voltage I see at this point is, as you can see here, about 24 millivolts. That's the same, close enough to what I was seeing without any load at all before. So this so far looks good. More gain is needed, because if I connect a 50 ohm load to the output, this is what happens. The transistor doesn't have enough current to support this voltage. But this is what I would have with a better amplifier, I mean more current capability. I need a better accuracy on the noise readout, so I have increased the bandwidth to something like 60 kilohertz, and then also change scale and averaging a bit. What you see here is the reference load, my quiet noise head, and here is the output of the low noise oscillator when there is no signal into it. And I see 0.17 dB difference. I now have two J310 in parallel, and this is the level out from the amplifier, 0.029 dB. And here is the noise floor with the cold noise head, that's my reference, minus 0.007. Noise is much lower. The gain is a bit lower because I have 22 ohms in series, but the drop of noise is much larger than the loss of gain. With 10 dBm on the signal frequency, the level I see here is unchanged. I had to change the tuning capacitors significantly, means decreasing them. Now, if I put the 50 ohm load on the output, like this, the signal level is not much affected. The two FETs can drive 50 ohms. The power is only 14 dBm, 14.8, well 15 dBm. It means that the gain now is only 5 dB. I need a 1-to-2 step-up transformer to get sufficient gain. That would add 6 dB to give me 11 dB. Now I have 5 transistors in parallel, and the impedance is very low on the sources, so I have put here a 1-to-2 step-up transformer to give me 6 decibels of power gain. I had to put an extra resistor in parallel with the drain resistor because otherwise I couldn't tune it because of the big capacitance between the gate and the drain, the Miller effect. So I had to put a resistor there to make the drain more close to ground or for RF. I will use a bootstrap later on to make the drain capacitance disappear, but that's a second, well, it's a coming experiment. First I want to look at the noise of this. The impedance I see is like this, and I'm spanning a very narrow frequency range, but you see when it starts here it's close to 50 ohms. So I should be able to measure this on the low noise amplifier. I can just check span 0.1 megahertz, and then you can see it stays at 50 ohms, and then it makes some exercise, only a few points, and then it stays at 50 ohms again. Span 1 kilohertz is more appropriate. For 10 dBm input, the level I see on the 1pf capacitor is a little bit lower, but not a significant amount. Here is the selective amplifier now, 0.31, and here is the noise floor of the noise head, minus 0.01. So I have 0.32 dB of noise increase now. I have reduced the DC supply from 25 volts to 8 volts, the same as I had with fewer transistors. The current is 53 milliamps now, and these are the noise properties that I see. Here is the 50 ohm reference, and I can read it from here to here, minus 0.02. And here is the low noise amplifier. This is most annoying, minus 0.02, and now it is I wait a little bit more. I don't know the reason for this. I will have to look for it someday. It's here then. Point 11, point 12. So it is now 0.14 dB. So it is much better. The increase of the noise floor, for example 0.17 dB that I had with 2 transistors. Sorry, that was with a single transistor. That means that the noise floor increases by a factor 1.04, which means that the noise that comes from the amplifier is 0.04 times of the total noise. But the gain is 0.91 due to the resistor. So that means that the noise contribution from the active devices is 0.044. With 2 transistors it was 0.012. With 5 transistors operated at 25 volts, it was 0.019, so not quite as good as before, but at a lower voltage it is much better. It's 0.008. It's almost nothing. So I cannot get much power out because I cannot increase the voltage much, but I can put a transformer to step up without loading, and then I can find some kind of power amplifier that is a low noise, hopefully. Correction, the output is of course from the source and not from the decoupling capacitor down here. This is what the amplifier looks like now. I have added a bootstrap, that's an emitter follower. It uses 3 times MPSH10 with this diagram and a 10 ohm resistor. There are easily oscillations in the VHF or UHF range to bring the voltage of the source, which is also here 10 ohms, to attenuate high frequencies. It brings it back to the drain, which means the drain will move with the same voltage almost as the gate, meaning that the gate to drain capacitance is no longer very important. This allows me to use a smaller tuner capacitor on the filter that I haven't shown here, because the capacitive load of the gate to drain capacitance affects the filter tuning significantly. The output, I take it from the sources of the JFETs, and I do that through a series resonant filter, because loading here with something wideband will cause oscillations. But loading it with this kind of low Q series resonator makes this thing stable. And then I step up the impedance by a factor of 4 with this 2-to-1 transformer. And this is the output. First I will look at the voltage at the output of the crystal filter. And it looks like this. So it's reasonably high, like before, and that is with 10 dBm input power. And here is the output impedance, pretty close to 50 ohms, and this is in a narrow range, only 1 kilohertz. I make it wider, frequency span 0.1 megahertz, and then it stays for quite some time at a little bit above 50 ohms, and on the resonance it is 50 ohms. So this is good enough for measurement purposes, and it's also probably a good source to amplify. I have been looking at the output on the crystals through this 1PF capacitors. Now, that is currently loaded by 50 ohms from that instrument. I will remove these components and retune, because the 50 ohm resistor introduces a little bit of noise. Here is the frequency response of the unit. Gain is now 12 dB almost, and impedance on 10 megahertz is 60 ohms, but on all frequencies it is reasonably close to 50 ohms. The bandwidth is, it tells me the Q is 79,000. The phase derivative is from 29 degrees to 86 degrees in 50 hertz. 29 to 87 or 86. This is the output impedance. It's pretty close to 50 ohms. Scale 0.2, enter. You can see here. Here is my room temperature 50 ohm load from here to here at very close to 0, because I calibrated it like that, of course. What you see here is the output of the amplifier, and I think I have statistics enough now. So from here to here I see 0.132, and here I had minus 0.004. So let's say 0.13 dB. That's the noise increase compared to a 50 ohm resistor of the 50 ohm output impedance from this amplifier when connected to the crystal filter that I have described earlier. At 0 dBm input, I see, as you can see here, 11 dBm output, and I increase in steps of 2 dB, and here the second harmonic becomes significantly bigger. It's 6 dBm here, but it's only 15 dBm, so there is some compression. This amplifier cannot deliver more than about 5 dBm output, but the filter can accept about 15 dBm at the input. So that is 14 dB higher. I need an output amplifier that can deliver much more current. The maximum input is about 14 dBm, and that's the power capability of the crystals. More crystals in parallel would improve this a little bit, but going from 8 to 16 would give only 3 dB. Output, if current were available, would be 26 dBm. The noise floor is 0.14 dB above the noise figure 5.5 dB of the low noise amplifier. 0.14 dB means 1.033 times, so the excess noise is 0.033 times above minus 168.5 dBm per hertz. That comes from the noise figure of the low noise amplifier. That is minus 15 dB, so assuming perfect circumstances, noise should be 9.5 dB below minus 174 dBm per Hertz. We always have the thermal noise when we have a 50 ohm system. So noise should be 1.11 times above minus 174. That would be minus 173.5 dBm per Hertz. For 14 dBm input, the output should be plus 25 dBm with an appropriate amplifier that I do not yet have. So noise should be at minus 173 plus 25 is minus 198 dBc per Hertz. We will see if this is possible or if I have made mistakes here. I don't know yet, but I will try to reach this kind of performance.